So, in the last few classes, we have been trying to take an approach based on differential equations to understand fluid motion. We only derived the governing equations, one of them the fact that mass is conserved, there is a mass balance, we express that as a differential equation. The second one was the momentum balance, or force is equal to mass into acceleration. We represented that fact also as a differential equation. Now, we should learn how to use these equations for the kind of problems that we want to analyze, but before that there is one more balance that we often use, and that is about energy, right. The energy is conserved, or there is an energy balance. So, one can use that fact also and write down an equation that can be quite useful. Now, we will not do it as rigorously as we did for the mass balance and for the momentum balance. We are going to only do it so that it looks very similar to something that you are already familiar with, and that is Bernoulli's equation. Okay. So, we are going to see how energy conservation is nothing but similar to what you already know, the Bernoulli's equation, and how does it get modified really for a real fluid flow. So, we are going to now look at Bernoulli's equation. We will try to derive that. Okay. So, let us say you have some flow field. So, that means there is a velocity, there is a pressure, and let us also in general assume that the density is also changing, so that we do not have to restrict ourselves for incompressible fluid flows. And let us say we will consider a differential element. So, for this particular one, we are going to really write down just energy balance as a 1D equation. Okay. So, we will not consider therefore a cubic element, we will consider something simpler. Let us say a fluid element, okay, which is made of, which is actually a stream tube. I will explain what is a stream tube. Let us say that is a stream tube. Stream tube is something that is made up of streamlines. So, you take the surface of the stream tube, the surface of the stream tube is made up of streamlines, or made of streamlines. What are streamlines? Streamlines, so if you know a streamline, and if you draw a tangent at a particular on the streamline, that is actually going to give you the velocity field. So, let us draw some streamline. Okay. Let us say that is a streamline. If you take a particular point and let us say a tangent there, that is actually going to give you velocity field. If I take another point and draw a tangent there, so let me draw the tangent with a different color, that. Okay. So, that is going to give me the velocity there. If I have here, that is going to give me the velocity field here. Okay. So, streamline is essentially connected by those velocity vectors. So, if there is a change in the direction of the flow, streamline will show that. So, you can draw streamlines at every point in the flow field. So, stream tube is basically a surface made up of such streamlines. So, for us that means that if this is what the stream tube is, if I take any point and draw a tangent, that is basically going to be the direction in which the fluid is flowing. There can't be a fluid motion that is perpendicular, because by definition streamline is the one which is drawn such that the velocity is tangential to it. Okay. In other words, if you consider a stream tube, because there you can't, that is made up of streamlines, there cannot be a flow from in or out. So, there is a flow that is going to go in, okay, and there is a flow that is out. So, this is in, that is out. So, this is like really a tube, and then there is fluid that is coming from the left side, and then the fluid is going to go outside, but on the surface, because it is made up of stream tube, there is no flow through the surface. So, it is the stream tube is as if it is like a rigid object for that matter, because there is no flow that is going to go through the stream tube, but it is really made up of fluid element. Okay. So, that is the stream tube that we are considering. Let us say this side the pressure is P, density is rho, velocity is V, and outside it is P plus dP is the pressure, rho plus d rho is the density, V plus dV is the velocity, and there is a change in area. So, there could be a change in area because fluid need not just go straight, fluid probably would be expanding and flowing like that, the fluid might be flowing like that. So, you have a inlet area, let us say A, and let us say the outlet area is A plus dA. So, this is the system under consideration. And what we will do is we will write down a mass balance and a momentum balance for this particular fluid element that we have considered. So, we already know how to do it. We can say that the mass in minus mass out should be equal to rate of change of mass in the system. So, if you think about mass balance, so mass in minus mass out has to be equal to rate of change of mass inside, right. So, what is the mass that is flowing into the system? That is going to be volumetric flow rate times density, but volumetric flow rate is nothing but the area times velocity. So, rho times A times V is the mass that is going in minus the mass that is coming out is going to be rho plus d rho times A plus dA times V plus dV, and that has to be equal to the rate of change of mass, which is del by del T of the mass in that area. So, let us say in that volume. So, the volume is given by some area times particular length. So, let us mark the length also. Let us say from the center to here the length is given by ds, okay, and also let us say that this is actually at an angle theta with respect to the horizontal. So, the rate, so the volume of this is going to be approximately equal to A times ds times density is going to be the rate of change of mass in the system. So, this is nothing but really change in rho into A into V. So, let me rewrite it as differential of rho into A into V with the minus sign, because it is left minus right, is equal to del by del T of rho into A times ds. Okay. Or for the given element, we could therefore write it as del rho by del T times A into ds is equal to minus d of rho V times A. So, A is a particular area that you have considered and d is the total length of the differential length of the fluid element that you have considered. Okay. So, that is what the mass conservation equation gives you. So, now we will write down the linear momentum equation. So, linear momentum equation is nothing but again momentum in minus momentum out has to be equal to the rate of change of momentum, but we also know that the rate of change of momentum can come from forces. So, we could write that in momentum minus out momentum has to be equal to rate of change, but that rate of change can also come from all the forces acting in the system. Remember, that is a fact that we used to write down the momentum conservation equation. So, for this particular fluid element that we are looking at, okay, so there is a force that is coming from pressure, there is gravity that is acting, and then there could be viscous forces, and then we can also calculate what is the momentum that is going in, what is the momentum that is going out. Okay. So, let us start with the right hand side. The rate of change of momentum can be written as del by del T of momentum of the fluid. So, that is mass. Okay. So, that is density into volume times V. So, that is the rate of change of momentum in that volume, that is equal to the differential of the momentum in minus momentum out. So, just like the mass conservation, we can write it as basically minus d times rho into A into V, which is the volumetric flow rate, times V, sorry, the mass flow rate times V, which is the momentum flux, okay, or momentum flow rate, plus sum of all the forces acting in the system. Now, here we need to write down what are the forces. Okay. One obvious force is the body force. Okay. So, the body force which is coming from gravity. So, what will be the body force? Is nothing but just the weight of the system. So, here we have A as the inlet area, ds is the length, and what? And then gravity is acting downwards. Only thing is that, so gravity is acting downwards, but the element is actually up like that at a particular angle. So, we need to find out the component of gravity that is acting along the ds direction. Okay. So, this is the direction that we are trying to see now, that is the direction. Okay. So, we are writing down the force balance in that direction. So, in the direction of that pink arrow. So, we have to find out what is the component of gravity that is acting along it, and that is going to be nothing but, so because gravity is acting downward, okay, so that is the direction in which gravity is acting. So, it is going to be g sin theta that is going to act in that particular direction. So, body force is going to be area times length, ADS is going to give you the volume, times rho, volume times density, that is the mass, times g sin theta, and it is acting, so g is acting downward. So, it is minus g sin theta because it is acting at an angle theta with respect to the horizontal. Okay. Now, so let me make a smaller diagram here. So, that is the direction in which g is acting. That's a kind of fluid element that we were really looking at, and we said that is nothing but ds, right? The length of the element. Let's say this in edge, okay, from a particular base is at a height z1 and the out edge is at a height z2. So, if I make a triangle there with that angle theta, so this is ds, this is z2 minus z1, let me call it dz. Then sin theta is equal to dz divided by ds, or ds sin theta is simply dz. So, I can use that ds sin theta here and write this as minus a rho g times dz. Okay. So, that is what the body force is. Now, we have got surface forces. And we know that surface forces are two types. One is pressure, the other is shear stress. Okay. What we are going to do is we are going to neglect shear stresses. So, we know that shear stresses is basically arising from viscosity, or it is due to friction. So, by really neglecting shear stresses, we are talking about frictionless fluid. So, if there is a fluid which was not having any viscosity, okay, it does not feel any friction, that was the case, then there is no shear stresses, and that is the case that we are going to look at, and then we will correct it later on how to account for friction. So, the only force that we are, the surface force that we are worried about really is the pressure force. So, let me make a diagram again to tell what is the best way to do it. So, that is our diagram that we are looking at. We said there is an inlet pressure and then there is an outlet pressure. So, P, there is a P that is acting on the inlet and there is a P plus delta P that is acting at the outlet, but we know that it is only the difference in pressure that is going to create a force, and therefore, let us say that the force at the inlet, okay, or the pressure here is 0 and the pressure at the other side is simply dP, because dP is the one that is going to really constitute the pressure. Here we have an area A and here we have an area A plus dA. Okay. So, the net force acting is simply going to be dP times A plus dA in this manner, right. But the point is that if you write it as A times dP plus dP times dA, and we are looking at really a differential element where any of these differentials actually the values go to 0, where dP goes to 0, dA goes to 0. So, this quantity is going to be much smaller than AdP, or in other words the effective pressure force that is going to act is going to come mainly from AdP. So, look at this, when I write down the force, okay, this is the force arising from pressure, force from pressure is what I have calculated, which is basically based on the inlet side and the outlet side, but there is actually a pressure contribution that is going to come also from the periphery, okay, from the lateral sides. I have neglected it because that is again going to be a small number, and you could actually show that that is going to be much smaller compared to the contribution that I have identified here. Okay, but let us not worry about how to show that at the moment. Let us see that it is A into dP is the net force that is going to be acted, and that is going to act in the direction opposite of your ds, and therefore, the pressure contribution is going to be nothing but minus A into dP. So, putting all of them together, we have minus A rho g dz, that is a force. So, what am I substituting? I am substituting it here. Okay, I am substituting it into that expression. I have the force, I have the change in the momentum and the rate of change. So, minus A rho g dz is the force, minus A d p is equal to minus, we have sorry, plus d into rho A v v plus d into A rho v square plus del by del t of rho into A into v ds, rho into A into v times ds. So, that is the expression that we have. Let us expand this. Now, if you look at the mass equation that we have derived, which is that del rho by del t times A ds is equal to minus dou rho V A, or equivalently del rho by del t plus times A ds plus d times rho V times A is equal to 0. Okay, so we have got the right hand side. So, we are going to now simplify the terms on the right hand side using the product rule. So, for convenience, this I will write it as d of rho into A into V times V, which is d into rho A V times V plus rho A V into d V plus then is what you have as this part. Then here this is going to be del by del t of rho into A V ds plus A ds into del into rho into del v by del t. So, as far as time differentiation is concerned, A and ds are constants. So, rho into v is what I need to really differentiate. So, I have taken the derivative of rho with respect to time times everything plus the differential of velocity with respect to time multiplied by everything. Now, if you go back and look at your this can be written down or let us look at the continuity equation. So, if you look at the continuity equation, you will see that del rho by del t into A ds is minus d rho v into A, or it could also be written as del rho by del t into A ds plus d into rho v A equal to 0. And you can identify these two terms in this equation. So, you can identify that del rho by del t into A v ds and d of rho into A into v. Okay. So, these two terms are exactly the terms that you have in your mass conservation equation, and therefore, they basically add up to 0, and what you have left is now A rho ds into dou v by dou t plus rho A v dv plus A dp plus A rho g dz is equal to 0. We will cut our A from all of them, and therefore, we get dou v by dou t times ds plus I will divide throughout by density v dv plus dp by rho plus g dz is equal to 0. Okay. So, this is really an unsteady Bernoulli's equation written in a differential form, or if I integrate it, then I could write it as dou v by dou t ds integrated from some S1 to S2 plus v dv integrated is really v2 square minus v1 square by 2, that is integral of v dv, plus integral dp by rho integrated from p1 to p2 plus g of z2 minus z1 is equal to 0. So, this is if I integrate from point 1 to point 2. Now, if I take the assumption that let us say we are worried about steady state flows or steady flows, okay, where time dependency is not there, then I will not consider this term, and I will also say that rho is a constant, and if rho is a constant, I could take rho outside from this integral, and therefore, this integral is just integral dp is nothing but p2 minus p1. So, we get v2 square minus v1 square by 2 plus p2 minus p1 by rho plus g times z2 minus z1 equal to 0, or writing in a nicer form p1 by rho plus v1 square divided by 2 plus, or we will write p1 by rho g plus v1 square divided by 2g plus z1 is equal to p2 by rho g plus v2 square by 2g plus z2, and that is the familiar equation that is called the Bernoulli's equation, right. Now, let me just tell you the assumptions that went in deriving that equation, because that tells you when you should be using Bernoulli's equation. Okay. So, we started of course with a simple differential element. We are actually doing in a 1D fashion. We are just worried about the direction which we called as ds. We calculated the mass balance, we calculated the momentum balance, and the first assumption that we made is about the frictionless fluid. Okay. We said the fluid has no friction. Okay. So, that is one that is important, because then that means Bernoulli's equation should be applied only when your fluid has really no friction. Now, the second assumption that we made is that it is applicable only for steady flows. Third is that we are assuming that the density is constant. Okay. So, these are the three cases, these are the three assumptions that have really gone in deriving the Bernoulli's equation. Now, so let's see what this means. Okay, or let me just give you this. So, pressure, this first term is typically called pressure head. Okay, this is called velocity head, and then of course then height. Okay, some height. So, head really means some height. So, why is it called before that? So, what are these terms? Okay, so this is really nothing but the pressure work or the work. Okay, so the work is done by the pressure, right. So, whenever the fluid is moving, pressure is a force that is acting, and there is the fluid is moving. So, there is a force times velocity that gives rise to a work in the work on the fluid. So, P, this first term really represents that work that is done on the fluid, okay, represents the potential energy. So, this is really kinetic energy, this is really potential energy, and then there is a pressure work. So, it says that if you look at pressure work and kinetic energy and potential energy, that sum remains constant, okay, along any point that you, along any streamline that you consider. Okay. So, if you consider two different points and write down the kinetic energy plus potential energy plus pressure work, if the fluid has no friction and if it is steady state and is incompressible, then you can apply Bernoulli's equation, and that is why this is actually an energy balance. So, this equation that we have derived really is an energy balance. Yeah, so the other thing that I wanted to tell is about pressure head. Okay, so what would be the units of pressure head? Bernoulli's equation right now the written it's in a way it's written that you have an Z1. So, this quantity now has the dimensions of length. So, the equation should be dimensionally homogeneous, okay. Each term should have the same dimension. So, Z1 has the dimension of length, then V1 square by 2g should also have the dimension of length, and you can verify that. Similarly, pressure by rho g will also have the dimension of length, okay. So, this equation now is written in such a way that each term such as pressure head, velocity head, all of them have the dimensions of length, okay. So, we are really expressing energy in terms of length. So, for example, when you have potential energy and you say, oh, the potential energy is really dependent upon the height, at a particular height it is. Similarly, kinetic energy is expressed as a height, pressure work is also expressed as a height. Now, therefore, if you say that your fluid is actually not frictionless, but there is a friction, okay. So, if it has friction, that means that certain amount of energy is lost due to frictional forces, okay. Because of frictional forces, some energy is converted into heat. So, in other words, the action of viscosity between fluid layers result in generation of heat, okay. Typically, that number is very small, and therefore, you will not worry about the number need not be small, but if you actually convert it into temperature, that may be very small. So, typically, you do not consider temperature variations, but still there is an energy loss, okay. So, we can say that if you had a pressure head, a velocity head, and then there is a potential energy and a part is lost due to friction, then you will say that there is a head loss in the system, okay. So, for a frictional fluid, you can say that your equation is really P1 by rho g plus V1 square by 2g plus Z1. Let us say that is the energy that is in, is equal to P2 by rho g plus V2 square by 2g plus Z2 plus a quantity HF, which we will call now as a head loss, okay. So, that is energy that is lost in the system, okay. So, you can see that that loss would essentially be a positive quantity, because there will always be friction invariably. So, that particular number or the particular quantity that comes up will always be positive. On the other hand, let us say if you are applying this equation to a pipe, okay, a long pipe, and then you have fluid in, which you will call 1, and then you have 2. Then you can actually apply Bernoulli's equation between point 1 and point 2, and you could write down the equation, where now you have to say what is the HF, or your idea most of the times would be to find out what is HF. On the other hand, let us say if you put a pump, okay, some pump in between. So, that is a pump. What does the pump do? Pump would give you energy into the system. So, one way of writing it is that if you want to write, you could say you have an HF, then you can say minus H pump, okay, because HF is the loss in energy, pump is going to give you energy into the system. So, you can again talk about a pump head, okay, or head thanks to the pump, okay. So, that energy that is input into the system, you can call it a pump head. So, typically we will worry about that equation. If you have a pump, you know how to add it, or if you have something which is extracting energy, like for example a turbine. So, then you have to remove that turbine head, okay. So, depending upon what you have in the system, you can keep adding or subtracting different heads. So, that is really the energy balance.